In this video, I will be showing you how to convert from base n numbers to decimal. Now, some rules. We need to multiply each digit from right to left with the base raised to n, where n starts from 0 and increases by 1. Now, all we need to do is add all these products to get the decimal value. So, let's record. You have there 5,481 in decimal. Now, we can represent this in some other way. Now, if we take 1 and multiply it by 10, which is its base, raised to 0, we get a 1. Remember, anything raised to 0 is 1. Next, we get an 8. The 8 we multiply by the base of 10, raise that to 1. We get an 80, and then we multiply 4 by 10 raised to 2, we get a 400. 5, we multiply by 10 raised to 3 to get 5,000. Now, in the rules, it said to multiply by the base raised to n, and n starts from 0, and we increase it by 1. That's why you see there 10 raised to 0, then 10 raised to 1, 10 raised to 2, then 10 raised to 3. For larger numbers, you just have to increase the powers. Now, with these products, all we need to get is the sum. That's 5,481, which is what we started with, since this is the decimal number system. This is the set of rules we're going to be following for the next few numbers. Okay, now let's take another example, and we're going to be converting from binary to decimal. Now we have there 10111 in base 2. We're going to be converting it to decimal. So we start with the first one. We multiply that by the base raised to 0, so we still get a 1. Then the next bit, we multiply that by 2 raised to 1, we get a 2. The next bit is 1, we multiply that to 2 squared, which is 4. Then the next one is 0, we multiply that by 2 raised to 3. Now, if it is 0, you can disregard that process. Just make sure to take note of the powers. Now, lastly, there's another bit there, which is 1, and we multiply it by what? 2 raised to 4, which is 16. Now, after that, we sum up all the products to get 23. So there you have it. You have 10111 in base 2 is now 23 in decimal. Okay, now next example. We have 2,375 base 8, and we want to convert that to base 10. Okay, let's start with 5. So we multiply that by what? 8 raised to 0. So again, anything raised to 0 is 1, so we still get a 5. Next, we have 7. The 7 multiplied by 8 is 56. Now 3. Now 3 multiplied by 8 squared. 8 squared is 64. So we get 192. You don't have to use a calculator. All you can do is just mentally multiply 64 by 3. So you get to multiply 3 by 4. That's 12. 60 multiplied by 3. That's 180. 180 plus 12 is 192. You can also use a piece of paper. Next, you have 2 raised times 8 raised to 3. Now 8 squared is 64. We multiply 8 to that to get 8 cubed. That becomes what? 512. So multiplying 2 by 512 will give you 1024. Then you sum up all the products, you get 1277. That's your answer. So 2,375 in base 8 is now equivalent to 1,277 in base 10 or decimal. Okay. Now the next example is converting from 25A8 base 16 to base 10 in decimal. So we start off with multiplying 8 by 16 raised to 0, which is still 8. Then we have A. A is equivalent to 10, right? So 10 multiplied by 16 raised to 1, which is 160. Next, we have 5. We multiply that by the square of 16. Now, what I do is 16 times 16 is simply 16 times 6 plus 16 times 10. So that's 16 times 6 is 96, and 10 times 16 is 160. Now 160 plus 96 is how much? 256. Further, what I do is, if it's 256 multiplied by 5, what I do is I multiply the 6 by 5 first. That gives me 30. And 250 is easy enough to solve when you're multiplying by 5. That's 1,250. So 1,250 plus 30 is 1,280. Next, you have 2. Now 2 times 16 cubed. Um, well, you can always actually do it this way. 16 squared, as you know, is 256. Now you're going to be multiplying that by another 16. Maybe it might be easier for you to multiply it by 2 4 times. So, example, 16 squared, 256. Multiply it by 2 raised to 4, because 2 raised to 4 is 16. So now, anyway, if you want to do it some other way, that's fine. Now 16 cubed is 4096 multiplied by 2. So after that, you get the product 9640. So again, you have 2588 in base 16. That's now 9640 in base 10, or in decimal. Okay. Now, again, the same rules apply for any base. So if you're going to be converting from any base going to decimal, all you have to do is multiply each digit starting from the right with the base raised to n, again starting from 0 and increasing by 1. Now, I'd like to discuss some shortcuts between a few of the bases. You have the binary, the octal, and the hexadecimal. These are quite important to anyone studying computer programming or computer systems, because these are the ones most commonly used. We have shortcuts for these, and I'll show you how to convert from one to the other in a few moments. But first, I'd like to show you uh, a background so that you can better understand it. Now, here you have a table. I've laid down the decimal numbers, binary, octal, and hexadecimal. So take note. The one that's complete here are the digits of the hexadecimal number system from 0 to F. Okay, so beside those are all equivalent values. Take note also that in the binary, I've written them down as 4-bit numbers. Okay, so again, if you try to look at them, you can pause the video and try to see everything's there, and they're all equivalent across each line or across each row. Now let's look at the octal and the hex. Again, hex has 16 digits, and the octal number system has 8. 8 is exactly half of hex. Okay, why do I need to tell you this? Because I'd like to ask you to look at the box that I have there. I've boxed the digits from 0 to 7 of the octal number system. Again, there are 8. Now the next 8 are from 1 0 to 1 7 down there. Exactly 8 again. Now these two 8s actually comprise all 16 of the hexadecimals on the right. Now, let's concentrate on the blue rectangle. 0 to 7, when you look at the equivalent in binary, have 0 0 0 down to 1 1 1. Now, the next box, the green one, when you look at the binary, they also start from 0 0 0 and go down to 1 1 1. Now, you will see a pattern, and that pattern repeats itself every 8 numbers. Now, beside those 3 bits, if you compare the blue rectangle and the green rectangle, the leftmost bit beside the blue rectangle are all 0, and the leftmost bit of the green rectangle are all 1s. Now, if you go further, all these bits outside the rectangle will start again to make their own pattern. So what's important to remember for now is that when we're dealing with octal numbers, again, we're dealing with a pattern of every 8 numbers. And those 8 numbers are comprised of 3 bits. Okay, so remember that, 3 bits. Now let's go to the hexadecimal. Now, there are 16 again, but when you look at the equivalent in binary, you will see from 0000 down to 1111. This is actually the pattern of the hexadecimal number system, every 16 numbers. Now, the binary equivalent of these 16 numbers are just 4 bits. Okay, so that's what we need to remember for the hexadecimal in binary, 4 bits. Now, let's go to the next slide. Again, remembering octal numbers, 3 bits, hex numbers, 4 bits. This will be important when we convert from one number system to the other involving octal, hex, and binary. Okay, let's try to convert an octal number to a binary number. Okay, we have an example there of 2375 base 8. This is fairly simple. Again, octal, 3 bits, remember that. So what we need to do is just convert each octal digit to its equivalent 3-bit binary number. So 2 is 010, 3 is 011, 7 is 111, and 5 is 101. So you are given now 12 bits. All you have to do is just put them together. Now you have 10011111101. Take note that the leftmost 0, I can still put that there, or I can opt not to put it there because it's just 0. It won't affect the answer. Then finally, just write down the base number of 2 beside your answer. Let's have another one. That's 6146 in octal. So 6 is 110. 1 is 001. Again, it's important that at this stage, between bits, you really have to write down the numbers in 3 bits. Okay, now 4 is 100 and 6 is 110. Again, combining all of those, just write them down together. You have 110011001110 in base 2. Now let's try converting from hexadecimal to binary. Given 8D4 in base 16, what do we do? Remember, 4 bits if it's hex. So let's write down each hexadecimal digit into its equivalent 4-bit binary number, starting with 8. 8 is 1000 in binary. D is 1101 in binary. And 4 is 0100 in binary. Then all you have to do is write them all together. 100011010100 in base 2. Let's take another one. So you have 7B, C, D in base 16. We want to write that in binary. So starting with 7. 7 is 0111 in binary. B is 1011. C is 1100. And D is 1101. Now, writing them all together, again, you can get rid of the leftmost bit in the 7 because it will not matter. So you have 111, 10111, 100, 1101 in base 2. Now that we've converted from octal and hexadecimal to binary, let's see how to convert from binary to octal and hexadecimal. Starting with this. So let's say we have the number 1110, 111000, in base 2. Okay, all we have to do is divide these bits. Starting from the rightmost bit, count every 3 bits and place a line between the numbers. There you go. So every 3 bits, we draw a line. Okay, and what do we do with these? Now, those 3 bits, what you need to do is write down the equivalent octal number. So 101 is 5. 001 is 1. 110 is 6. 101 is 5. And 11 or 011 is still 3. That's your answer. Write it down as 35615 in base 8. Now, we use a similar process to converting from binary to hexadecimal, this time taking note of 4 bits at a time. So let's say we have this number. So we have 111, 0111, 000, 1101, which is actually the same number from the previous slide. Now, let's divide it into 4 bits starting from the right. So you count 4 bits, draw a line, then count another 4 bits, draw a line, and then count another 4 bits, and so on. Now, what you do is write down the equivalent hexadecimal number of those 4-bit binary numbers. You have 1101, that's D. 1000 is 8, and 1011 is B. 11 is 3. That will be your answer. That's 3B, 8D in base 16. So what we actually did was convert from binary to both octal and hexadecimal with the same value. So you will see there two different numbers in different bases, but they are all equivalent to each other. That's it for now. Thank you for watching.